A recap of yesterday's class. We started with electrochemistry, which is chapter 5 in the textbook, and it primarily deals with the process of electrolysis, which is the breakdown of an ionic compound or the decomposition of an ionic compound when it is molten or in aqueous solution by the passage of an electric current. In this case, the ionic compound that is being used for electrolysis is called an electrolyte, right? And the electric current is passed through the electrolyte using electrodes, which are made of either unreactive metals such as platinum or non-metals such as carbon in the form of graphite. And so they're inert and they do not react with the products of electrolysis, right? The desired products of electrolysis, let's say, in most cases. The electrodes are connected to a supply of electricity, and so the positive electrode is called the anode, and because it is the positive electrode, it attracts the negatively charged ions, and so those are called anions. The reason they're called anions is because they're moving towards the anode. Do not confuse the positive sign that will be given in a diagram on the anode and the charge of the anions. Anions are negatively charged. The anode is the positive terminal. So remember either one of these. It's easier to remember, oh, anions are negatively charged. They move towards the anode, and so opposites attract, and therefore the anode has to be the positive terminal. That's how I do it, at least. The negative electrode is called the cathode. It attracts the positively charged ions. Those are called cations. Again, the reason they're called cations is because they're moving towards the cathode. So remember that cations are positively charged and they move towards the cathode, and opposites attract, so the cathode has to be negative. General guidelines for electrolysis: non-metals are produced at the anode, hydrogen gas or metals are produced at the cathode. At an inert anode, chlorine, bromine, iodine, which are the halogens, are produced in preference to oxygen. So if you've got an option between the two, you will go right, and you're asked which one will be produced, it will be the halogens. At an inert cathode, an inert is important, right? Let me underline that as well, because we will see the process of electroplating and purifying copper, and so in those cases the anode will not be inert. So at an inert cathode, hydrogen is produced in preference to metals unless unreactive metals such as copper are present. So if you've got a choice between hydrogen and a reactive metal, then as we will see today, it will be hydrogen that's produced, not the reactive metal. And then, right, substances that conduct electricity to a small extent when in molten state or solution are called weak electrolytes. Substances that do not conduct electricity when in molten state or solution are called non-electrolytes. Electrolytes are able to conduct electricity because when molten or in solution, the ions are free to move. Ions are charged particles and they're moving to the electrodes. And the reason they're able to move is because the electrostatic forces, attractions between the ions are weakened. We talked about the electrolysis of lead to bromide. And so the lead ions and the bromine ions were separated. Lead ions moved towards the cathode, bromine ions moved towards the anode. And so you had this compound that was split into its constituent elements. So this is the reaction taking place at the cathode. Lead is gaining electrons to become elemental lead. Bromine is losing electrons to become a bromine atom. And then two bromine atoms were joining together to form the bromine molecule. As you would expect from halogens, they are diatomic molecules in the elemental state. The transfer of charge during electrolysis in general is due to the movement of electrons in the metallic or the graphite electrodes, the loss or gain of electrons from the external circuit at the electrodes, and the movement of ions in the electrolyte. So the electrodes have delocalized electrons and the electrolytes has ions, and both of these contribute to the flow of electricity through the electrolysis setup. Now, continuing, today we will take a look at the electrolysis of aluminium oxide. So as you've already seen in the reactivity series of metals, aluminum or aluminium, whichever pronunciation you prefer. There's a difference between the American and the British. So aluminium is a very reactive metal. And any react, like the very reactive metals, whether it's sodium or magnesium or potassium or aluminium, right? What happens is wherever they're present, they do not stay unreacted because they are very reactive, right? They react with other elements to form compounds, right? And those in many cases are oxygen, right? So often it's oxygen. They react with the oxygen in the air to form oxides. Right? Often. So aluminum is the same, right? So aluminum ores, one of them is called bauxite, right? Which is Al2O3. It is aluminium oxide. And because it's an ionic compound, it is difficult to extract. So you need to make it go through the process of electrolysis to actually extract the aluminium from this compound. So the first step is to purify. So bauxite has many impurities with it. All right, so first you need to purify the bauxite. Remove all other impurities, whatever you have, other compounds, other elements that are attached to it, and just get the pure aluminum oxide. The reason you need to do this when you make it molten, right? It has improved conductivity. So the process of electrolysis will be more efficient. Again, we are talking about pure. Okay, so once you've done that, then it is dissolved in a compound called cryolite. So the purified aluminium oxide is dissolved in cryolite. Cryolite is this. Oh, sorry, not. Okay. So sodium and aluminum bonding together with fluorine. And what this helps to do is it reduces the temperature at which electrolysis needs to, occur. It reduces the melting temperature. So we know, right, impurities reduce the melting point of a substance. That is why when you add salt to ice, then right, even below 0 degrees centigrade, it will stay as water, because you need to, uh, its melting point is reduced. So its melting point is actually gone below zero. Right? That's the case for ice. Now the question is, well, why did you bother purifying it if you wanted to add something that will, have the effect of an impurity? And the thing is, right, all the impurities that bauxite has from its ore, if you don't purify them, then they will interfere with the electrolysis process, and they will, right, because they will reduce the conductivity of aluminium oxide. Cryolite has the same effect as an impurity, but it does not interfere with the conductivity of aluminium oxide. So it's sort of a win-win situation, right? So this cryolite, it reduces the melting temperature of aluminium oxide without interfering with its conductivity, right? Unlike other impurities. Okay, so once that's done, so it mentions, right, that the melting temperature of aluminum oxide is 2017 degrees centigrade, and from there cryolite actually brings it down to between 800 to 1000. So that's, it brings it to half or less than half of the melting point, which is great in terms of energy, right? So you need to use less energy uh, to melt, right? You need to put in less heat to melt aluminum oxide, and so you're saving energy. Okay, what happens after that? Right, molten the molten mixture which has cryolite and uh, the aluminum oxide is electrolyzed. Right, the anode and cathode are made of graphite. Okay, so what happens is uh, the negative, right? So when you split this up, when you see which ions this has, right, you have these are the ions you have. So In fact, it's not an equation to balance. So these are the ions you have. You've got the aluminum ion and you've got the oxygen ion. So this guy will be moving towards the anode, and this guy will be moving towards the cathode. And so what do you expect to see at the anode? Well, you will have oxygen losing its electrons. So at anode, okay, now let's balance this. Aram, would you like to try?
Isn't it already balanced?
No. The reason it's not balanced is I think you're confusing this 2 with this 2. The subscript 2 tells you how many atoms of oxygen there are.
Oh,
The superscript is telling you the charge, so they're two different things.
okay. Like we have to add the two
Where?
on the reactant side.
Okay, so now we've got two atoms, right? But then what about the electrons? How many electrons will there be?
Two
No,
on the product.
no. See, a single atom of oxygen has two electrons, extra electrons. So two atoms of oxygen will have
One.
eh,
Sorry, like I don't know. Like
one atom of oxygen has two extra electrons. So it will lose two electrons. One
yeah,
atom will lose two electrons. So if there are
mhm.
two atoms, how many electrons will they lose in total?
Four.
Four. Now it's balanced.
Oh,
Okay. So you have oxide ions giving you oxygen molecule and electrons. Okay. Then what about aluminium, right? So at the cathode, you have aluminium that is missing three electrons. It's got a +3 charge,
yeah.
and you, in fact, right? How many electrons does it need?
Two.
Eh?
Sorry, wait a minute. It needs like six.
Why does it need six?
Sorry, wait a minute. Like it needs two.
Hmm?
Two.
How many electrons has it lost? The oxidation.
Um, my
Look at the oxidation number.
three.
3. So, right, it has lost 3 electrons. So, how many electrons does it need to go back to 0?
Uh, three.
Exactly.
Sorry. Yeah.
So, you have the aluminum ion, right, plus electron, giving you the aluminium atom. Okay.
Yeah.
And so, what happens is that the molten aluminium in the setup, the diagrams given in the book, obviously. And so the molten aluminium settles at the bottom of the the electrolysis setup, and then it is taken out by a siphon, so it is removed, and then all the other junk. Now what happens, there's a problem in this setup, and the problem is the oxygen that is being produced at the anode. So the anode is made up of graphite, which is carbon, and then you've got oxygen being produced. And so what happens is at the anode, some, like, it's a slow process, but still you have the carbon of the anode itself plus the oxygen gas, and they will react to form carbon dioxide gas. And so what happens is, over time, right, the anode is worn out, right? It burns away. And so it needs to be replaced. So, right, graphite is inert in most cases, but when you've got something like oxygen, it will, right, there's heat, and so, right, it will react with the oxygen to form carbon dioxide, and obviously, right, because the anode itself is made of carbon, graphite, it will react, it will, you will need to replace it because you're losing, physically losing the anode. Okay. Uh, and so we've already talked about, they give an acronym, right? You can see that this is a case of oxidation, and this is a case of reduction. And right, we know that oxidation is a loss of electrons and reduction is a gain of electrons. And over here, what they do is they give you an acronym. So you take the first letter of these words, and what you get is oil rig. So in case you ever forget what's happening in oxidation, what's happening in reduction in terms of electron movement, then oxidation is loss of electrons. So oxidation is loss and reduction is gain of electrons. All right. Any questions?
No.
Achha. What else? So the overall equation that you have in electrolysis that's happening is you have Al2O3. All right, and I balance this out for you, and you're getting 4.
Can I try?
You want to try?
Oh, I have already done that.
Okay, you can try the oxygen.
Like 6,
Yeah. Well, not 6 exactly. It is 6 here. 2 3s are 6, and so you've got 2 over here. So what will make the 6th?
3.
3. Right? And this is coming in as a liquid. It's molten. This is a gas. This is also a liquid because it's molten. And so aluminium oxide via electrolysis
Yeah.
is being converted to its constituent elements. Then they go on to tell you the uses of electricity, the uses of aluminium. It is lightweight, and it has good electrical conductivity and thermal conductivity, and so it's used in various processes, etc., etc. And because electrolysis is a process that heavily depends on electricity, and so, right, it is conducted in regions where cheap electricity is available, for example hydroelectric power. So wherever there's hydroelectric power, they will set up these purification plants.
Like, does the process of electrolysis help us in reality as well?
Happen in
Help us in reality as well?
help
Like, in,
us. Well,
yeah,
well, you have used aluminium foil. You probably have aluminium utensils at home to cook food. I don't know if you ever traveled in aeroplane, right? Aeroplanes are made up of an alloy of aluminium,
yeah.
right? The soda cans that you purchase are made of aluminium, and so where do you think all that aluminium is coming from?
But that, oh, yeah. Correct.
right? It is coming from the purification of it is coming from the aluminium that's extracted via electrolysis from its ore, bauxite, and that's just one example, right? You've got electroplating, which we'll talk about later, right? So, electroplating or other uses, right? Purifying copper as well. Copper is used in all the electric wiring, and your fans and heaters and all the other electronic gadgets. Hopefully, they're using copper, and so copper is obtained from via electrolysis as well, right? So
Yeah.
yes, they also go on to talk about the environmental. So I'm not writing that down, right? They talk about the environmental problems with the aluminium extraction and the right. So what happens is wherever this plant is, all the impurities are removed, and so they form red mud, right? All the impurities, right? And so they basically end up polluting the area where this process is happening. And then the cryolite is, it escapes into the environment as fine dust. And so obviously it will have a polluting effect and possible health effects because it's fine dust. And then, right, uh, environmental aluminium is claimed to be linked to Alzheimer's disease, which is a disease, a degenerative brain disorder. So your brain starts to shrink, right? And so even though they're saying that evidence is inconclusive, there's reason to believe that there's a link between aluminium and right so and this disease. So or right, at least it causes the onset, meaning it causes the disease to begin. So right, everything has its pros and cons. So as useful as aluminium is for us in our daily lives everywhere, it has its drawbacks as well. So I haven't written that down on the whiteboard. It is given in the text. You can read that. There's nothing technical about that. Next up, mm, electrolysis of aqueous solutions. So I think I can cover just a bit of this. And the first that we're going to talk about is the electrolysis of dilute sulfuric acid. So what's happening is you take water, and water itself is a very poor conductor of electricity. Right? And so if you try to perform the electrolysis of water directly, it's not going to happen. Okay. So even though it's saying the electrolysis of dilute sulfuric acid is basically, the electrolysis of water, right? But you cannot electrolyze it directly. So you cannot perform electrolysis directly. And it's understandable, right? Because water is a covalent molecule. And electrolysis depends on ionic molecules. So you don't have any ions for, to move in water. And so what you do is you add dilute.
Can you please tell that what are covalent molecules?
Covalent molecules are one that undergo covalent bonding, so they share electrons, right? They don't transfer electrons, as opposed to, for example, sodium chloride, which loses an electron, and chlorine, which takes the electron. So it's giving an electron to chlorine. So that's ionic bonding. So when you make this molten, like we've been talking about, you make the ionic compound molten, or you make an aqueous solution, so you dissolve it in water, and so, right, the ions will separate. But water itself, even though it has a polarity, right, it is a polar molecule, but that polarity is not going to help in electrolysis, right, because it is a covalent molecule. Does that help?
Yeah.
So what we do is we add dilute sulfuric acid, right? And sulfuric acid is ionic, so it is H2SO4, and so you've got two hydrogen ions and a sulfate ion, right? And so what that's going to do is that's going to help with the electrolysis. The setup, right? We'll talk about. I'll show you how the setup is. And so what you get through this, the products that you obtain are oxygen gas, obviously, and hydrogen gas. And the reason why you're adding dilute sulfuric acid is because, right, H2SO4 is ionic, and so it will, allow for electric conductivity. So what's happening at the cathode? What are the, okay, let's first look at what ions do we have possibly. In fact, in this case, okay, you only have hydrogen and, so what's happening at the cathode? You have hydrogen ions, right? And they are taking up electrons and forming hydrogen gas, hydrogen molecules. So that's H plus E minus, giving you H2, right? How does this balance out?
Binding two on the reactant side.
Well, right, it also works like this. So you got two hydrogen ions taking up electrons. So one electron, because you can see a single plus sign with the hydrogen, that means it needs one electron. So each of the hydrogen ion needs one electron to form the hydrogen atom, right? So
Yeah.
if you break up this, right, it will be right, it's going to form two hydrogen atoms, and then those hydrogen atoms will combine to form the hydrogen molecule.
Yes. Oh, sorry.
Okay, in the book, for some reason they've given four. They've doubled this, so it's 4H plus and 4 electrons, giving you 2H2, right? So for some reason they've given it as doubled. Now, right, because electricity is passing through this, and so that's going to affect the water molecule. On its own, right, water was not able to conduct electricity, but now that you've added dilute sulfuric acid to it, right, the electricity that is flowing through the solution is obviously affecting the ions of the sulfuric acid, but they're also affecting the ion, the water molecule. And so what's going to happen at the anode, right, first of all, is the water molecule is going to split into, so due to passage of electricity, the water molecule splits into H plus and OH minus. Okay, then, right, the at the anode, the hydroxide ions now, so we're not dealing with a base over here, right? We're not dealing with an alkali. It's not sodium hydroxide that you would expect. You add an acid. So where are the hydroxide ions coming from? They're coming from the splitting of water because of electricity. And now those hydroxide ions are going to move towards the anode. And what you're going to get, I'll write it out first, hydroxide ion, right, is going to give you water plus oxygen plus electrons. So it seems kind of odd, right? But the thing is, because water was split because of electricity, it can, go back. So what you're having over here is OH minus giving you H2O plus O2 plus electrons. You want to try and balance this?
I like we have to add 2 on the reactant side. Oh yeah,
Just two?
yeah. I
Hmm.
can, because like there are 2 hydrogens and 2 oxygens.
But nine. So on the reactant
And
side, on
like there are 3 hydrogens.
no, see, you have, on the reactant side you have one hydrogen and one oxygen. On the product side you've got two hydrogens and three oxygens.
Yeah.
So you need to be a bit more, you need to think a bit more about that.
Uh, we are.
See, if I put two over here, it's going to balance the hydrogen, but it's not
Yeah.
balancing the oxygen. And I don't have anything else, so it's all I have is the hydroxide ion. So that's not going to work.
Yeah. Uh, I cannot seem to process right now.
So balancing can be tricky,
Yeah.
right? Instead of directly trying to balance over here, you see, okay, what else can I do? So you turned this twice, and so now you've got four hydrogens and then two oxygens here and two oxygens here, so that's 4 and 4, and so that makes this easy. You just add 4 in front of the hydroxide ion, and because each hydroxide ion is going to lose one electron, four hydroxide ions are going to lose four electrons, and so you balance the electrons, and so this is what you're getting.
Yeah. That was easy.
Easy, you say?
Yeah.
Okay, so they mention that generally when aqueous solutions are electrolyzed, hydrogen is produced at the cathode, and we've mentioned this already in the general guidelines. And non-metals, right, other than, except for hydrogen, because hydrogen is also non-metal, right, are formed at the anode. And that is right. So because the examples we've seen so far, we've seen aluminium, which was, right, not aqueous, it was molten. And then we saw lead bromide, which was again molten, it was not aqueous, and so that's different. When you have an aqueous solution, right, so something to note, when you have an aqueous solution, generally hydrogen is produced at the cathode, and non-metals other than hydrogen are produced at the anode. But then keep this in mind, the guidelines, right? Hydrogen is produced unless there's an unreactive metal such as copper. In that case, hydrogen will not be produced, the metal will be produced, right? So in this case, you had hydrogen only, that was the cation, that was the only option, and so, right, there was nothing else to take preference. Okay, now I don't know, I feel like we haven't covered as much as I was hoping today. There is the electrolysis of concentrated aqueous sodium chloride. If you have a few, well, we do have 5 minutes. If you're up for it, I can cover it. Do you want to?
That's your wish.
Up to me, you say.
Yeah.
Hmm. Yeah, I think I'll do it. Okay. So we have concentrated sodium chloride solution. And so when you got sodium chloride concentrated, right, what are the cations and anions that you would have? So, right, this basically means that you have NaCl and water. So we know what's going to happen to water due to electricity. We already talked about that. And so which ions do you have? The cations. Or instead, let's look at it this way, right? From NaCl, right, you have the sodium ion and the chlorine ion. And from water, you're going to get the hydrogen ion and the hydroxide ion. So these are your cations, these are your anions. So what's going to happen at the cathode, right? You have an option between sodium and hydrogen. So we just looked at the guidelines, right? You're going to get hydrogen unless there's an unreactive metal. Sodium is very reactive, right? And so compared between sodium and hydrogen, hydrogen is the one that's going to easily take up electrons and go back to its elemental state, right? Because sodium is so reactive, it's not easily going to take up the electrons, right? It's going to stay as, right, whatever it is. So what you're right, so you're at the cathode, you're going to get hydrogen. So this hydrogen ion plus electron.
Cathode is a positive ion.
Cation is a positive ion.
Oh, yeah.
Because it's moving to the cathode is the negative terminal, the negative electrode.
Oh, okay.
And so because it's taking up electrons, it's being reduced, so that's reduction, and you are getting the hydrogen molecule. Right, so what's happening is H plus E minus giving you H2. This is simple to balance. You want to try?
We're gonna add 2 on the reactant side.
So two of these and then two, right? Two of these, and so you're getting a hydrogen molecule. So that's what's happening at the cathode, right? Again, the option was between hydrogen and sodium, and because sodium is very reactive, it's not going to easily take up the electrons, right? Hydrogen will easily accept electrons, and so hydrogen gas is produced. So sodium is very reactive, does not easily accept electrons, right? It easily gives up the electrons. Hydrogen easily accepts electrons. Okay, then let's move to the anode. So you have an option between the hydroxide and the chlorine. Okay, and right, the chlorine is more ready to release its extra electron as compared to the hydroxide. So Cl minus readily releases or gives up electron because it is, right, the minus means it has an extra electron, so it's giving up that electron compared to the hydroxide. The hydroxide does not readily give up its electron, and so you would expect, right, chlorine is a gas, so chlorine gas is produced at the anode. So how is that happening? That's Cl minus giving you Cl2 gas plus electrons. Balance that, please.
We have to add 2 on the reactant on the product side.
On the product side?
Oh, sorry, on the both sides.
Okay,
Like
both sides. So I've added 2 over here. Where do I add 2 over here?
for E
For the
for
electron.
electron.
Good. I was just waiting for that, whether you notice the electron or not. Okay. And so, right, the hydroxide ion is left in, right, is left in solution, and so that increases the concentration of the hydroxide, and we know this is what makes things alkaline, and so the solution around the anode becomes alkaline.
Alkaline is basic, no? Base.
It is a soluble base.
Oh yeah.
Okay, so yeah, just in time. And so I'll stop there. And so the next time we'll talk about the electrolysis of copper to sulfate, aqueous copper to sulfate. Right, so that is one where the electrode is used up. Then we'll talk about fuel cells, and then finally electroplating. So hopefully the next class will complete this chapter. Any questions?
No.
Then I will see you next time, inshallah.
I love this.
Allah.